I'd like to talk for a couple minutes about the reaction types that you need to know. The reaction types, the major reaction types that Chapter 4 talks about are listed over here on the right side. Precipitation, acid-base, and redox. Excuse me. But if you took 101 here at Front Range, or probably any other chemistry background that you had a different set of reaction types. And so I want to talk about how those different classifications kind of interact with each other. So first let's talk about what we call a double replacement reaction. This can also be called a double displacement. It can also be called metathesis. It's kind of the old name for it. And double replacement reaction means we have two sets of partners who are going to trade partners. So similar to this, let's take silver nitrate and let's add some potassium chloride. We're going to put both of those as aqueous, dissolve them in water, because a lot of things that react don't react if you don't put them in water, because they parts never find each other. Not always necessary, but often. And so the positive ion and the negative ion on each of our compounds are going to trade partners, and of course the positive have to go with the negative because that's what attracts to each other, and then we have the potassium nitrate left over. In this case, silver chloride is going to be our precipitate. It turns out that this is a precipitation reaction, but wait, we just said it was double replacement, right? Okay, here's the deal. Our precipitation reaction is one kind of a double replacement reaction. The other major kind of double replacement reaction is HCl plus NaOH. What does this look like? Why? We are swapping partners again, of course, and we're putting the H, I'm going to write it kind of funny, with the OH, and we already know that compound as water, right? Same thing. That's really water. But HOH kind of emphasizes that here's the positive partner from one compound, the negative from the other, the positive from this one, the negative from that one. They're swapping partners and forming the new compound. In this case, it's covalent, so the charges go away. So acid-base is the other kind of typical double replacement. So we can put both of these in the double replacement camp. One kind of neat thing to know is, since these guys are swapping partners and they're keeping their same identities on the other side, these are always non-redox reactions. And that's kind of a nice thing, since that's going to be our next major category from Chapter 4 we have to deal with. Double replacements are always non-redox. Well, if we have a double replacement, we probably have a single replacement as well. So let's move on to that quickly. A single replacement reaction is called, in your book, it's called, just towards the end of the chapter, they refer to displacement reactions. And those are otherwise known as single replacement in most places. So what we're going to do in a single replacement reaction is we're going to have a metal by itself. And we're going to have usually a metal. It could be hydrogen also, but let's do it with a metal. And let's put another metal, but this one's in a compound. Okay, now in this case, this metal that is by himself is going to kick the metal that's in the compound right out of the compound. So I kind of draw this arrow to show him kicking out the silver from the compound. So magnesium is going to form a compound with chlorine. Magnesium says, get out of here, I am going to bond with the chlorine. So when magnesium bonds with chlorine, it doesn't bond in a 1-to-1 ratio like the silver did. Text message, go away, sorry. I should turn my phone off before I do these, shouldn't I? Magnesium chloride, so it bonds in a 2-to-1 ratio, so we have to put the coefficient, the subscript in there, sorry. And then, where does the silver go? Well, he's all on his lonesome. He's been kicked out of that compound, and so he precipitates as a solid. So this is a useful kind of thing. You can use this for plating like plating one metal on top of another metal, like silver plating something or gold plating something to put the expensive metal on the outside where people can see it and keep the cheaper metal on the inside, or for a whole variety of other purposes. This is an interesting reaction. It is always redox, for one thing. If you find a single replacement reaction, it's always redox, in keeping with the rule that I think is very helpful that they mention in Chapter 4, that says anytime you find an element by itself that is neutral, and it on either side of the reaction in a chemical reaction, that will always be a redox reaction, because the oxidation number of the element when it's by itself will be, of course, 0, and when it gets into the compound on the other side, it won't be 0 anymore, it'll be something, in this case -2. And so since it's changing, it's going to be a redox reaction. Since this silver is in a compound on the left side, it has +2. Did I say minus? Oh my goodness. Since the silver is in a compound, it's a +1, and it's going to become a 0 on the other side because it's by itself. So anytime you find an element by itself in a reaction, it's going to be a redox reaction. Single replacement reactions happen with a strict pecking order. So you look in your book and in this section, and you will find something called the activity series of the metals. And any metal that's higher in the activity series can kick any metal that's lower in the activity series out of the compound. So magnesium is higher in the activity series than silver. Therefore, this reaction happens. If I had written it the other way around, silver plus magnesium chloride, I would look in the activity series and I would find that silver here is lower in the activity series than magnesium, is lower on the pecking order. He cannot kick magnesium out. And so therefore I either put an X on the arrow to show it doesn't go, or I put no reaction or something like that. It's not going to happen. So using that activity series of the metals, any metal higher can kick another metal that's lower out of a compound and replace it in the compound. The one that's kicked out has to go off by himself, and any lower metal can't do that. All right, then very quickly, the other types of reactions I think that are mentioned in the book are pretty straightforward. We have combination and decomposition, which are really opposites of each other. And so when things decompose, you think of them falling apart. When things combine, you think of them coming together. So we can take any compound that we can form from two pieces, whether they're elements or compounds, it doesn't really matter. I can take sodium plus chlorine and make sodium chloride. Now, I'm not balancing everything. You notice here that this isn't always balanced. My magnesium up above isn't balanced. This one isn't balanced. You can balance it. But I am combining something. Should I balance it? Oh, why not? Let's put a 2 in there. We can go back up and do the other one too, for that matter. It's probably bothering somebody, so let's do that. Okay. If not, it'll probably bother me. Okay, so decomposition, we could take salt and decompose it, and we could make it into sodium and chlorine. And this would involve the use of electricity to try and make it decompose, but combination, we're taking two things, making it into one. Decomposition, taking one thing, making it into two. There's a plus sign here and a plus sign here. That means that we have more than one thing on that side. And then the last one is combustion, in which you have any kind of fuel plus oxygen reacting. And usually we're talking about an organic fuel, not always. We could in some senses think of iron rusting, iron plus oxygen making iron oxide as a combustion reaction. But typically when you think of combustion or burning, you're thinking of some kind of a organic compound with carbons and hydrogens in it, and it's reacting with oxygen from the air, and we typically make carbon dioxide and water if we're getting complete combustion, which we always want to have, at least. In this case, to balance it, we need to stick a 2 in there and a 2 in there. So this is methane, which is what you burn in your furnace if you have a natural gas furnace. But this is combustion. And do we have an element by itself? Why, the oxygen's by itself. So, of course, this is, again, a redox. I should mention that combination and decomposition, because we don't always use elements, sometimes we're combining compounds, are sometimes redox and sometimes not. So you have to be careful about that. Just write sometimes not. Okay? So check them out to see what they are.